just written a paper on.
Sorry about that.
And yeah, that's all right. And I'll just give you an outline of, you know, what my story is, because my story is a little bit different to most people and how they get into the field. So I started my story at the University of Sydney. I studied science law. So my major was in pure maths. And then once I finished, I didn't use that side so much. I actually went and started a business doing something more on the legal side, actually immigration law. So I actually had 2 startups, which you can see the logos of there. So I ran them for quite some time and then sold out and thought, okay, what do I do next? Did a bit of traveling, went around the world. So you can see down the bottom there, that's a picture of me in Patagonia. So I spent like a bit over a year just traveling around, just trying to think about what to do next. And I started reading a bit about quantum computing, and it just seemed to me that this is one of the areas where there's just so much potential to really make some big advances that are going to be interesting and have far-reaching consequences. So I went and talked to Stephen Bartlett, who you see the picture of there, and we just got to talking. I read through Nielsen Chuang, and I think that's how a lot of people get started. And yeah, I worked on this paper with Stephen and with Ben Brown, who you see there, who's very well known in the quantum error correction community and has a lot of papers that are very interesting. So just finished my first paper and put it up on the archive, and this is it. It's quite a long paper, so really this is a bit of an ad for the paper. I'm really hoping after this you can get some interesting ideas and sort of get motivated to pick the paper up and have a look. And so today what I'll be talking about is really just an overview of what are the main implications of the formalism, what is it, and what can you do with it. And then the second part of it is really just diving a little bit deeper onto a couple of areas which I think might be interesting to you guys. It's to do with looking at the algebra of the XP operators and finding the logical operator structure of codes. And I'll be taking a bit more of a mathematical approach because I think we have some mathematicians in the audience. So I might just focus a bit more on the maths behind it and give you a bit of a flavor about how it works. But really, I'm quite interested to find out what your impressions are of the work, and you know, any ideas that occur to you or any questions that you have on the way through. Please interrupt me and ask questions. I really like it when people ask questions, and that gives me a good idea about what you guys are finding interesting and what I might need to explain more carefully. And I've got to apologize for my accent. I've got a bit of a strong Australian accent. So if if you can't understand what I'm saying, please tell me that as well. Please, I can certainly explain things a bit more slowly if that's what I need to do. Okay, so what I'm going to start with is just to dive back into the Pauli Stabiliser Formalism, which is what's normally known as the Stabiliser Formalism. And I just want to talk about what it is and what are the features of this formalism that we really like and that we'd like to replicate in a generalization of such a formalism. So really, how I see it is that one of the main points of the Pauli Stabiliser Formalism is that you can much more efficiently represent quantum states and understand some of the non-classical behaviors of quantum states. And really what's behind that is that if you want to represent a general quantum state on n qubits, you actually need a lot of information. You need 2 to the n complex variables to represent a state, a general quantum state. So instead of that, we can represent some states as stabilizer states. And what we mean by that is that we specify a number of independent Pauli operators, which we call stabilizer generators. And our state is just the simultaneous +1 eigenspace of those Pauli operators. And the kinds of operators we can choose for those stabilizer generators are basically elements of the tensor product of the I times the identity XZ group. And we can represent those as binary vectors of length 2 times n + 1. So instead of an exponential amount of complex variables, we now have a polynomial number of discrete variables. So we can represent states a lot more efficiently using this stabiliser formalism. And we can do a lot of really nice operations. The mathematical structure of the stabiliser formalism is really nice. So basically we have efficient algorithms, basically which just use linear algebra over Z2 for determining the code space, by which I mean an independent basis of code words, finding the logical X and logical Z operators, which tell us what protected operations we can do on that code space, unitary evolution via Clifford operators, and measurement of any Pauli operator on the code space. So in that sense, we have what we call the Goddessman-Canal theorem, which means that, well, basically these states are all classically simulable, which is nice. And so if we're going to generalize this formalism, we'd like to extend those algorithms as much as is possible. And most of the talk today is talking about to what extent we can reproduce those algorithms in our new formalism. And can we express more states? And so you might say to yourself, well, that all sounds really great. Why would we bother extending the Pauli stabiliser formalism if it's also nice as it is? And really the three things that I would say about that is, firstly, we can only represent a very limited set of states. And we were talking before about topological phases which have non-abelian anyons. And in particular, we can't represent them within the Pauli stabiliser formalism. And in a lot of ways, they're the interesting ones that we'd like to look at. Secondly, there are a lot of no-go theorems that we have for the Pauli stabiliser formalism. And I think here largely about the no-go theorems regarding self-correcting quantum memories, for instance. So it'd be really nice if we could extend the formalism a bit and look for codes which do have this self-correcting property. That'd be really nice. And finally, because everything in the Pauli stabiliser formalism is classically simulable, in a certain sense, we don't really capture anything that's non-classical. I mean, we can see superposition and we can see entanglement, but really all of that can be classically simulated. And so getting to the heart of what it is about quantum computers that goes beyond what we can do classically, somehow we're missing it. And so I think this is one of the really interesting implications of this work, as maybe we're getting closer to understanding this non-classical behavior in this formalism. Okay, so let me tell you about the new formalism that we're proposing. So basically, it's the same as the Pauli stabiliser formalism, but this time, instead of just X and Z operators, we're going to allow tensors of X operators and basically arbitrary rotations around the Z axis. So what we do is we fix a precision, which is an integer n greater than or equal to 2. And our stabiliser generators are now from a different group, a broader group in general, which is that group that you see there, the tensors of omega I, X, and a diagonal P operator, where we set omega to be a 2nth root of unity, and we set the P diagonal operator as being basically a 1 over n rotation around the Z axis. And so every time you choose a different capital N precision, you get a different formalism. So if you choose big N equals 2, you just get back the Pauli stabiliser formalism. And if you choose big N equals 4, you get back the XS stabiliser formalism in that paper there by Nee, Boyer-Sharpat, and Van der Nest. So basically, that's the paper that got me headed on this direction. And a lot of the techniques are extending the techniques which are in that paper and extending the formalism again. So the first question is, if we take this formalism, which new states do we get? And first of all, the easiest one to look at is our single qubit states. So the question here is, which states can we represent in each of the formalisms? So let's have a look first of all at the Pauli stabiliser formalism, which I think of as an XP formalism with capital N equals 2. So this is a very famous diagram. I think you would have seen it many times before. It is from the original paper on magic state distillation by Bravi and Kittier. And basically it says that within the stabilizer, the Pauli stabilizer formalism, we can represent anything which is in that first diagram, which is basically two pyramids joined at the base. So anything within that octahedron we can represent within the formalism. So if we now take big N equals 4, so we're now in the XS stabilizer formalism, we're in the middle picture. So this time we have two pyramids, but this time instead of a square base, we've got an octagonal base. And we can represent anything within that, I don't know what you call it, double pyramid with an octagonal base. And you'll notice there that there's some very interesting states that we can represent in the XS formalism. For instance, the eigenstate of the TXT inverse operator, which happens to be a magic state from that original paper. So you can see that this formalism naturally supports magic states. Though it's not all swings, there's some swings and roundabouts there. It's not all upside. You do lose some operators you would like, as we'll explain in a minute. I'm certainly not claiming you get universal quantum computation using these codes. So in the limit, as we increase n to an arbitrarily large number, you can see that we get all of the states within that double cone structure on the right. So if you make n big enough, you can potentially get to any of those states on the circumference of the circle there. So basically that tells you within the single qubit states what you can potentially get within the XP formalism. So as you can see, that's quite a lot wider than what we have in the Pauli stabilizer formalism. So if we now ask the question, okay, give me as many qubits as you want, what states can I make? Well, probably the best way to think of this is in terms of graph states. So there's a really famous result in the Pauli stabilizer formalism that basically all of the stabilizer states you can make in the Pauli stabilizer formalism are up to local Clifford's a graph state. So what do I mean by that? Basically, what I do is I take a graph, which you can see a diagram of up the top there. And on each of the vertices of that graph, I put a qubit. And I initialize my state in the plus state, tensor it up n times, where n is the number of vertices. And I can apply a control Z operator on all of the vertices in each edge of the graph. And yep, pretty much that tells you which states you can make within the Pauli stabilizer formalism up to local Cliffords. So if we now ask the same question for the XP stabilizer formalism, we get a much broader range of states as we expect. So basically what we have now is what I've termed a weighted hypergraph state. And basically there's an equivalence between XP states and weighted hypergraph states. So I'll explain what a weighted hypergraph is. It's quite a lot broader than a graph state. So what you do is you have a graph, again, with qubits on our vertices, but this time our edges can include any number of vertices between 1 and n, the number of vertices. So here you can see an edge. The shaded part is an edge with 3 vertices. And here you can see an edge, which is a good old-fashioned edge just with 2 vertices. And apart from having what we call a hypergraph structure, we also have a weight on each edge. So you can see here that we have a weight of 1/4 for this edge and a weight of 3/4 for this edge. So basically what we do this time is for each of our edges, we apply a controlled P to the Q operator, where Q on n is the weight of each of the edges. So the edges can all have different weights, and you just apply that controlled phase operator to create our weighted hypergraph state. And so in the paper, we've got a result that says that up to a certain type of embedding into a larger Hilbert space, every weighted hypergraph state can be represented as an XP code. And conversely, up to this embedding operation, every XP state can be written as a weighted hypergraph state. So that pretty much tells you exactly what you can make in terms of states within this particular formalism. So probably if we're thinking about, how does the new formalism compare to what was known already, probably the closest analogy would be to the qubit stabilizer formalism. So this is basically where you allow yourself to set a qubit dimension D, and then have a certain number of qubits n. And in the stabilizers, you have generalized X and generalized Z operators within this qubit formalism. So that's quite well defined. And these papers here tell you about what those formalisms are about. So with the XP formalism, you see that we also specify the number of qubits. So this is a qubit formalism. So we specify, say, n qubits. But this time we specify precision n. So the parameters are kind of analogous to the qubit case. So one of the big differences we have between the qubit formalism and the XP formalism is that there's no notion of a generalized Hadamard. So the way I think of Hadamards is basically you swap, if you apply a Hadamard, you swap the X and the Z components of your operators. And so in the qubit formalism, we do have a generalization of the Hadamard operator. It's basically the quantum Fourier transform. But for the XP formalism, we don't get that. And that's because the X component and the Z component are not symmetric. So we only have X operators, we don't have fractional X operators, but we can have fractional Z operators. And that's a really big difference. And when I said there's a big trade-off, this is really the big trade-off when you're thinking about what states you can represent, what you can do. But what is also interesting, though, is when we look at commutators. So here I'm talking about group commutators. In the qubit formalism and the Pauli formalism, the group commutator is always a phase times the identity. But that is not the case for the XP formalism. And that's has quite interesting implications, because we can have commutators being arbitrary diagonal operators in the XP formalism, which is quite interesting. And so again, when we're specifying codes in the qubit and Pauli stabilizer formalism, we always require that our stabilizers commute. But, and this is something that was pointed out in the XS paper, that's not necessarily the case when it comes to the XP formalism. And in fact, in general, our operators will commute up to a diagonal operator. And so long as we don't have minus identity in the stabilizer group, we can usually define a code space. And so a couple of other things. Next, the code space dimension is fairly predictable in the qubit stabilizer formalism. But in the XP formalism, what we get is much more complicated eigenspace structures. And so what we see is that it is very difficult to predict what the code space dimension is going to be. And so in the paper, we look at how many different code space dimensions we get for a certain number of qubits and a certain precision. And you can see that it's a very wide range of possible eigenspace dimensions. And so because of that, it's really hard to predict what the code space dimension is going to be. And lastly, we have the simulation of measurements. In the qubit and in the Pauli stabilizer formalism, that can be done for any generalized Pauli operator, and it can be efficiently simulated. And a really big difference for the XP formalism in that is that that's no longer the case. And we'll talk a little bit more about that in a minute. So in the paper, what's there? Yeah, well, it's quite a long paper, so I'll give you the brief summary. So basically, we set out the framework first, and we try to translate all of the algorithms that we have for the Pauli stabilizer formalism across. So we've got an algorithm there for determining the code space. So what are the code words of the code? In the XS paper, they can only do that for certain limited classes of codes. We've got a general solution there. So that's quite an advance on what was there before. And it's tractable in many cases. We can do that efficiently in many cases, but the general case is actually an NP-complete problem. So if you have a reasonable number of logical qubits, it's quite efficient. And so the way I think of it is, for a small code, you can do this efficiently. For a large code, that's not guaranteed. But you can see what's going on with the small codes and extrapolate. There's an algorithm there for converting between the XP stabilizer state and the weighted hypergraph state representations of states. We've got algorithms for determining the logical operator structure. And the interesting thing about that is you don't just get the logical X and the logical Z operators. You can get all sorts of interesting non-Clifford operators there, so long as they're transversal in the and of the form of an XP operator. And you can get a complete set of generators for the logical operator group, which is quite nice. And then measurements, well, basically, that's not guaranteed to be possible in the formalism. We can do that efficiently for diagonal Pauli operators, so tensors of I and Z. We have an efficient algorithm, which is basically a generalization of the algorithm in Aronson and Goddessman. There's a famous paper about that. And you can do that efficiently, and you're guaranteed to be able to do it. But that's the widest general set of operators we can measure. For general operators, there are a couple of things that happen. So firstly, estimating the probabilities of each outcome can be an NP hard problem. And that's because of the difficulty of determining the dimension of eigenspaces. But secondly, if you measure an operator, you're not guaranteed to stay within the formalism. So quite often, if you measure an operator, you end up with a state which you can't express as an XP code. And that's the secondary problem that we see when it comes to measurements. So one thing that I kind of like is I like playing with examples. And for this paper, I tried to code up as many of the examples as I could. And if you want to play around with those, or put your own codes in, you can do that. There's a package, a Python package, where all the examples are in there, so you can play around with it. So if you want to do that, I'd be really happy for you to do that. And if there's any bugs, please let me know about that too. But that's a good way to get started. I don't expect you to implement all these algorithms. I've already taken the trouble to do that for you. So if you want to play with some codes and test a few things out, you can do that. So just to summarize, we basically get a much broader range of states with this new formalism. We can represent some interesting topological phases. That's a result from the XS paper. They knew at that stage that they could represent topological phases which had non-abelian anyons, which is quite interesting, I think. You get much more complicated logical operator structures. So you can get logical operators you can't see, for instance, in the Pauli stabiliser formalism. Which might be quite useful for magic state distillation. And basically what we see here is with all of these algorithms, they start out reasonably efficient, say when we put the precision n equals 4, and where we have a small number of qubits, but they gradually get less and less efficient. So that kind of suggests to me that we're starting to capture something which is not easily simulatable with classical computers, particularly when we start looking at large codes with large precisions. In terms of open questions, I really wanted to spend a bit of time on this. One of the things I really liked about the XS paper is that they left a lot of nice, juicy open questions, and they were really good about doing that. And that was something I found really appealing about that original paper. And so I wanted to pass that forward and set out a few good open questions for people that were interested in working in this. So the first thing that is really a major open question is how do you do error correction for these XP codes? So in the XS paper, they showed that there was a commuting parent Hamiltonian for XS codes, and that you can do error correction. Basically, it was in over several stages, I guess. I think you could probably do something similar to that for the XP formalism. But what I'm thinking might be a good approach is that there are certain codes which are a generalization of all of these codes we've been talking about in a sense, which is a formalism called the code word stabilized formalism. And I particularly like the idea that they've got there for error correction, because what they show is that for these code word stabilized states, you can think of them as a single graph state, which is translated to create a code space. Basically, you mix a graph state with a linear code or a classical code, a binary code. And you basically, when you have an error, all of the errors translate along the edges of the graph, and you end up just with a string of Z operators. So it's almost as if the error correction becomes a classical problem. I haven't got my head around it yet, but it kind of looks like a good approach because we've shown that these XP states can be considered as weighted hypergraph states. We might be able to do something similar, and it might be a more elegant solution, which works well for, say, Y-style errors, for instance. I think magic state distillation is really interesting possible application. As I mentioned before, those magic states seem to arise naturally as part of the formalism as eigenstates of the XP operators of a certain type. And the paper I'm citing there basically says that CSS codes are optimal for Pauli stabilizer codes in terms of logical T operators and distance and all that sort of stuff. But the thing is that these XP codes are not Pauli stabilizer codes. So we may well find that there's some nice algorithms that are efficient algorithms for magic state distillation using these codes. That question of which topological phases we can represent within the formalism is quite a good one. And the paper I've cited there basically shows that within the qubit stabilizer formalism, we can represent all the twisted quantum double models with abelian anyons. So my question is, can we do something similar for the non-abelian case and look at which ones we can represent? Maybe all, but I don't know. Let's see. The no-go theorem for self-correcting quantum memories, be great to look at some XP codes that might have some nice self-correcting properties. And really what I'm looking at now is, now that we understand the logical operator structure of codes better, can we turn that around and start designing codes to have a desired logical operator structure, which might be XP codes? So that's what I'm currently looking at. So I'm thinking about LDPC codes and, things like that. See what we can build, what we can make in terms of nice transversal logical operators. So that's really the first part of the talk, just the overview. I think that covers like the main questions that I see going forward and kind of the main implications. I might just pause for a minute just to see if anyone's got any questions or comments at this stage.
No,
Seems okay?
I think I'm good, yeah.
Yeah, cool.
All right. I have a question. Maybe you have it listed in the, you don't have it in the list, but I was wondering if you have any state-independent contextuality in this framework for n, say, larger than 2 or odd case.
Yeah, I was talking to Angela, who works with Stephen on this, and I sort of explained what I was doing, and she said, yeah, you've definitely got non-contextual states here. So she definitely thinks that we've got something interesting in terms of that. But I must admit, I'm very much a beginner in that particular area, so I'm probably the wrong person to ask about that one. But yeah, really happy if there's some stuff you think I should be reading to get on top and thinking about that, I'd be happy to do that.
Okay, yeah, I was curious. So yeah, about the Clifford hierarchy here. So there are a couple of groups that we are looking at that are not Pauli groups in general, but they have like similar commutation relations and so on. And in the case of the XP formalism, so in the last the item that's last just the Clifford hierarchy item here. So what was it again that you were looking at in this item? Yeah,
I didn't really mention it because it's a bit out there. So basically, if we set the precision n to be something that's not a power of 2, what we're expecting to see is that we may get logical operators that are outside the Clifford hierarchy. And so I'm thinking, if I set the precision n to be 5, I might get a logical operator which is a 1/5 rotation around the z-axis, which, as far as I understand, is not in the Clifford hierarchy at all.
Okay.
Yeah, and I might get a control 1/5 rotation, for instance. You might get all sorts of strange things that we haven't really thought about using before.
Okay, I see. Thank you.
But in the example that I'll show, we know how to make operators at all levels of the Clifford hierarchy. And there's two examples in the paper where we demonstrate we can make a control to the nz operator and a arbitrary root of a phase operator. And I'll take you through those examples fairly briefly in this talk as well. Cool.
Okay, thank you.
No worries. All right. Well, what I might do now is I might take a deeper dive, because I know you guys are mathematicians. I thought, I'll talk to some brothers here and share some expertise and some background on the mathematics which actually underlies this formalism. So first of all, what I wanted to talk about is the algebra of the XP operators. So how do you do various algebraic operations? And that's important because I want you to understand the structure of these operators. And secondly, I just want to show you how to determine the logical operator structure of any XP code. And that's quite interesting because you do get these operators at various levels of the Clifford hierarchy. And I'll just show a couple of examples and talk about how these operators arise. So the first thing I have here is just talking about the algebra of the XP operators. So a really nice thing about this formalism is that each XP operator has a unique vector representation. So what we do in terms of representing our XP operators, because we have a phase component, an X component, and a Z component, so we can basically think of the phase X and Z as a vector of integers. And the way we make the operator is that we take our 2nth root of unity, omega, and raise it to the power of the phase component, which is p there. And then we just do tensors of the X and Z operators in terms of the X operator and the phase operator P. So it's very similar to how the Pauli stabilizer formalism works, but this time we're just talking about X's and diagonal P operators, and we just have a different root of unity that we're operating with. So it's really exactly the same as the Pauli stabilizer formalism. And so I represent the operators in this way, the P and the X and the Z. I just separate the components with a vertical line, and I specify the precision n here in front of the components. So that tells me that this is a precision n operator and this is the phase X and Z component. And so you can get this unique representation because omega is a 2nth root of unity. That means our phase is, you can consider that to be in Z2n. The X component is either 0 or 1, so that's basically a binary vector. And the Z component, well, that can be anything in Zn. And so you can consider that a vector in Zn. And when we're doing algebraic operations, we can multiply and do all the other nice operations that we want just by adding and multiplying these vectors component-wise. And we'll show you some formulas in a minute about how that works. But a really important component of that is that we express those algebraic operations in terms of this anti-symmetric operator, which is this D operator here. So basically how this D operator works is that we take a Z component, which is basically, you can think of as a vector of integers. And we basically just take the phase component to be the sum of the vector components. The X component is 0, so that means it's a diagonal operator. And we do the minus sign in front of the Z vector to create our diagonal operator in this way. So all of the formulas I talk about on the next page are expressed in terms of this anti-symmetric operator, which you can think of as kind of generalizing the symplectic product from the Pauli stabilizer formalism.
Okay, just to make sure, the qubit Pauli group is included there, right? In this, I mean, if you look at the if you look at the group generator, so you already have state independent contextuals because of that. So the groups are of even order. Okay.
Okay.
So the D operator is. So you said that this is related to the symplectic form.
Yeah, because you can pretty much express your commutators in terms of these sets cetera, loosely based on that. So basically, what I mean by that is, I want to express things like multiplication in terms of vector addition, plus basically a modification. In the Pauli case, it's just a phase, but in the XP case, it's actually a diagonal operator. Yeah. So what I want to do is express multiplication in terms of addition plus a little modification factor, which is where I'm sort of getting this generalization of the symplectic product from. Okay, and I'll just show you the multiplication rule here. So as you can see, if I'm multiplying two XP operators, which have these vector representations, I add the vectors, and this is my adjustment factor. So basically, I multiply the Z component of my first operator by the X component of the second operator and multiply by that result by 2. This is all component-wise. And this is the anti-symmetric operator. So it's a really nice, elegant formula for multiplying operators together. And when you generalize that, you can figure out a rule for powers of operators. So that's this nice, simple operator there, which again is basically, you can think of this as adding the vector D times, and this is our adjustment factor there. And our group commutators look like this. So basically, it's just an anti-symmetric operator of that kind. And this is what happens when we act on a computational basis state E, which is a binary vector in this case, with an operator A. That's what it does to that state. So based on these algebraic identities, we can actually, do most of our operations. And the nice thing is that with this unique vector representation, we can use linear algebra to do some operations quite efficiently. So it's quite a nice way to look at things. So I'll just do the example of looking at a group commutator now. So for precision n equals 4, I'm going to look at an example. And so in that case, our 2nth root of unity is basically the square root of I, so that when I raise that omega to the power of 8, I get back 1. And my diagonal operator is basically just an S operator, so that when I raise that P operator to the 4th, I get back the identity. So I'm just going to do this group commutator where my first operator is just X operator tensored 4 times, and my second operator is an S operator tensored 4 times. So in that representation, the vector representation I was talking about, this is what the X operator looks like, and these are what the components are. And the same thing for the second one. And when you do apply the formula, what you see is that all of these terms disappear. And that's a general rule that happens for commutators of diagonal operators, because what you see is that if A2 is diagonal, then this X2 is a 0 vector. And so this term disappears, that term and that term. So we're just left with this term. And when I substitute in the X component and the Z component, I get this operator, which turns into Z tensored up 4 times. So the real point of this exercise was to demonstrate that our group commutators are in general diagonal rather than just phases times the identity. And secondly, just to note that if we're talking about commutators of diagonal operators, there's actually a simpler rule, which we'll actually use both of those in the coming examples. So just note that. Does that make sense, that exercise?
Yes. Yeah.
Yeah. Cool. Good.
So in the standard Pauli formalism, there is this linearity, right? So you say the linearity is kept still, right? So we still have some linearity because these formulas in the even this linearity is you meant by linearity the formula inside the D, right? This linear computation happening here. And is this modulo 2?
Yeah, so the D operator, this part is modulo 2n.
Okay.
This
I
part
see. Okay.
modulo 2, and this part's modulo n.
Okay. Okay. I see.
So it's interesting. It does take you a while to get your head around this notation, but I think it's the most efficient one to use. But yeah, there's some implications that aren't that obvious when you first look at it. And let's have a look at the, say, commutator rule. If I'm talking about the Pauli stabilizer formalism now, with big N equals 2, then what you see is that everything in here is a multiple of 2.
Mm-hmm.
And so the implication of that is that this component always disappears because 2 modulo 2 is 0. But this component here can be modulo 4, is modulo 4, but it's always a multiple of 2. So that means that this phase always represents either +1 or -1. And so we do recover our familiar rule from the Pauli stabilizer formalism. But yeah, the fact that this is modulo 2n and this is modulo n, that can be a little confusing at first when you start working with this stuff. But yeah, it seems to work out quite nicely. Okay, well, I might move on to the logical operator algorithm. I don't want to really get too detailed here with the exact algorithm that we're using, but I just wanted to give you a flavor of it and just give you a hint of the mathematics behind the algorithm. And I'm going to look at a couple of codes you might have seen before. So the first one is the Hypercube Codes, which you might not have come across, but it has a really interesting logical operator structure. And we show how applying the techniques in the paper make it really easy to see the full set of logical operators for a given code, even if it's a Pauli stabilizer code. And the second one is the Readmore Codes. So this should be really familiar. What you'll see is that when we look at Readmore Codes through the lens of the XP formalism, we start seeing some interesting things. So I'm going to use that as my second example. The first one I wanted to explain, though, is how do the logical operators break down in the XP formalism? And it's a little bit different to how it works in the Pauli stabilizer formalism. So here I'm going to assume that I've got a list of XP operators, which is my G set. And basically, those operators are going to specify my code space. So in the paper, there's an algorithm then to turn that set of operators G into a canonical form, which you can basically think of as making those operators independent. And in Nielsen Chuang, when they talk about the stabilizer formalism, they do something similar. So what you want is to have a set of non-diagonal canonical generators and a set of diagonal canonical generators. And what happens here, and an important property of this canonical form, is that the diagonal subgroup of this group G is generated by the diagonal part here. And that's really important when we're trying to figure out the code space. So something that's really interesting about these codes is that, unlike the Pauli stabilizer formalism, the logical identity group can be different to the stabilizer group. And that is often the case. In the Pauli stabilizer formalism, in fact, the code space fully determines the logical identity group. Now, what I mean by the logical identity group is the group of XP operators which fix the code space, which fix all elements of the code space. So it acts as a logical identity. So in the familiar Pauli stabilizer formalism, that's just the stabilizer group. That's not the case in this formalism. And in fact, what you see is that the logical identity group is really the master group that contains all of the possible stabilizer groups for that code space. And in that sense, it's a maximal group, the logical identity group. The next group I want to talk about is the logical XP group. And this is really the group of operators that preserve the code space, but might apply some non-trivial action on some of the elements on the code space. So it's not a logical identity, it includes a logical identity in general, but yeah, it really does relate back to what we think of as a logical operator in the Pauli stabilizer formalism. And so in the paper, we've got algorithms to determine the generators for the logical identity in the logical XP group. And just to give you an idea what it's about, this is a little bit different to what's in the paper, and it's an algorithm I'm currently working on to perfect. But basically, you can show that an operator L is a logical operator if and only if it commutes with all elements of the logical identity group up to a logical identity operator. So back in the Pauli stabilizer formalism, the logical operators commute with the stabilizers full stop. So the group commutator has to be identity in the Pauli stabilizer formalism, but in this case, it has to be an element of the logical identity group. So it's a little bit of a different formalism there. And so now if we want to figure out what our diagonal logical operators are, we can use our simpler formula for the group commutator, which I talked about before, which is this anti-symmetric operator here. And we just require that that operator is in the logical identity group for all x, where x is the x component of the canonical generators. So yeah, that's basically just a basically like a linear programming task that you can do, and you end up with a list of all the diagonal operators, which can include our non-Clifford operators. And nice thing about that is, even for the codes that we know already from the Pauli stabilizer formalism, it gives us a much more complete view of them. And just to give you an idea about the mathematical structures behind those algorithms, so what we're talking about here is that a lot of our operations are on the diagonal component, which you might have noticed in the algorithm. And this time, we're talking about operations over a module. So basically, we don't have a vector space anymore. We've got basically a vector space over a ring, you can think of it. And so when you're doing that, things are a lot more complicated. You need to use the how basis. So I don't know if you guys have come across that. There's a paper that this guy wrote in 1986, how to do basically a generalize the idea of a basis from vector spaces into modules. And you can use that to determine kernels and all that sort of stuff. So basically, all of these algorithms use that how basis method to figure out these kernels and spans. And what I'm interested in, and this is an open question really, is, you know, how do we generalize the CSS construction into the XP formalism? So you can think of CSS codes in the Pauli stabilizer formalism the following way. It's basically all about, to specify code, you basically just choose two binary codes, which are linear codes, and they're generated by, say, an SX matrix and an SZ matrix. They're both binary matrices, so that your SZ is in the kernel of SX. And so if you do that, you've defined a valid code. And you can generate SX and SZ from cell complexes. So the general case there is that we generally put qubits on the edges, and then our stabilizers are determined by the face and vertex of that cell complex. Yeah, so any adjacent edges to the face, we put say a X operator on them to create a generator. And any edges adjacent to a vertex, we'll say put a Z operator to define our code. And then we can actually find our logical Z operators by taking the kernel over Z2 of SX and subtracting out the elements of SZ, which are trivial operators. So that's how we do CSS codes and logical operators in the Pauli stabilizer formalism. So it'd be really interesting to look at how that works for the XP formalism. because you can think of Sx and Sz as generalized components, but this time they're over different rings. So to my mind, I'm not exactly clear how that generalizes, particularly if you try to make them out of cell complexes. So I don't know if you guys have any thoughts about that, but I'd be really interested to figure that one out. That'd be quite interesting.
May I ask a basic question about the code spaces and the correspondence to the stabilizers?
Yep.
So when you have the code spaces in the XP formalism, are they uniquely determined by the IXP group? Is that?
Yes.
So, okay, so we have to look at that group.
So IXP and the code space are really very much corresponding. So each defines each other uniquely.
Okay.
Yeah, so there's definitely a correspondence there, very strong correspondence. Okay, I might just show you a few examples. So the first one I've got here is the Hypercube Codes. And this is based on a blog post by Earl Campbell. So what you do is you take a hypercube, which could be dimension D, you put qubits on the vertices. And our stabilizer generators, well, we put an X operator on all of the vertices. So you can think of that as being the single dimension D face. And we put Z operators on the vertices of each dimension D-1 face. And that defines a stabilizer generator for each face. And yeah, we can find the logical operator structure of those codes, and it turns out that they're very interesting. So what it turns out to be the case is that for each code word in the code, we can address it and apply a -1 face. And that basically gives us arbitrary control Z operators. And I'll show you an example here for D equals 3. So this is a dimension 3 hypercube, which is just a cube. So we have n equals 8 qubits, and our precision is also big N equals 8. And so our stabilizer generators are basically applying an X on each of the vertices, and for each face, we apply Z operators on the face. So there's 6 faces. So when you look at the independent generators, we end up with these ones. And so that defines 3 logical qubits. So this just basically tells you what the non-diagonal logical operators are and what the code words are. But when you look at the logical operator structure for the diagonal operators, this is what you find. So these are the generators of the diagonal logical operator group. And you can think of them as acting as a control Z operator on each of the code words along here. And this is the logical code word 0, 0, 0. And this operator applies a phase of -1 on that operator, on that code word. And you can see that for each of our code words, of which there are 8, we can individually address them and apply a phase of -1. And you can think of that as a control Z operator. And we can keep playing this game and adding more and more dimensions to create control to the n Z operators. We know we can do that. So it's really interesting now to look at what these operators are like in a more geometric sense. So I'm thinking here about our control Z operators. And so if you map them out, you see that they have support on all of the vertices of the cube. And what you see here is this is a T operator there, anything with a 1. And this set of 3s, they're all T-cubed operators. So you can see that, in a sense, all of our control Z operators are 3-dimensional. Now, if we have a look at our control Z operators, you can see that they're 2-dimensional and they have support on faces. So here you have T to the 6 and T squared. And then when we look at our logical X and logical Z operators, we see that our Z operators are actually 1-dimensional. And this is T to the 4 equals Z. Whereas our X operators are 2-dimensional, and you can see that these 2 operators are going to anti-commute like our X and Z operators should. So to me, it seems like there's a real fundamental connection between the dimension of the operator and the level of the Clifford hierarchy. And it's quite nice to notice that for this particular code. And I'll just briefly talk about the Readmore Codes. So I'm really interested in this as a basis for generalizing into, say, LDPC codes and looking for LDPC codes with a desired logical operator structure. And that's why I want to look at these ones. So first of all, let's talk about the 7-qubit Readmore code, which is basically, well, it's a Steen code. And you can think of that as three square faces meeting in a common point. And again, I have my qubits on the vertices. And our stabilizer generators, well, they're symmetric in X and Z. So I put X operators on each face and Z operators on each face, and I get 6 stabilizer generators. And you can also think of that as 2 classical simplex codes. Now, this code has really nice logical operator structure, very elegant. We've got transversal, the full transversal group. So we've got a logical Hadamard, logical S, and if we take 2 of these codes, we've got a transversal control Z. So really nice. So I'd like to try and generalize that and try to find LDPC codes with the same logical operator structure using this formalism to design them. And what I really want to see is that I can do a logical S on each of my qubits, and I can do a logical control Z between any of my logical qubits. So if I can find a code like that, I'd be very happy, but let's see if it's possible. But that's what I'm trying to do now. You can generalize that for any dimension, really. So here we're looking at the 15-qubit Readmore code. And again, you can think of that as 4 cubic faces meeting in a common point this time. And each of those faces meets in the square. And this time, what we do is we can make a code which is symmetrical, this time in X and S. So it's like the next level up of a color code, you can think of that. And so we apply S operators to each vertex of each face, and the same thing with the X operators. And you might notice that when I look at the commutator of those 2, it's exactly the same example we used before. And the answer for the commutator of, say, this face and that face is Z on these vertices in between. And what you see here is that that actually specifies the same code space as the Readmore code, which is a Pauli stabilizer code, which is defined on using X and Z operators only. So it's an example of that phenomenon I was talking about before, where we could have the same code space for 2 completely different stabilizer groups. So just an example of that. And the nice thing about this code is it has a transversal T operator. So my question is, can we find, say, an LDPC code which has a similar logical operator structure that might be symmetric in X and S? So yeah, that's what I'm trying to do now. And that's all I had in terms of presenting, but if there's questions about what I've talked about or any ideas that you guys want to talk about, I'd be happy to do that now.
Oh, so was that it?
Yeah, that's all my presentation.
Well, I'd like to thank Mark first, just while he's just finished. I'll do the clap. Any questions? Okay. Yeah, I just wanted to ask a clarification point. You had mentioned something about the outcome probabilities for like the measurements that these, what was the issue there again? I was kind of interested in that, but I didn't quite catch it.
Yeah, so the thought experiment I'd use there is, let's say I create a plus state. So plus, and then tensor it up, say, n times, and I make n really big. So n could be 100, say.
Okay.
All right. And now what I'm going to do is I'm going to measure a series of diagonal operators.
Mm-hmm.
So when I do that, if I do a lot of them, that becomes an NP hard problem to determine what the dimension of the code space is.
Mm.
So in the Access paper, they talk about that, and they gave an example of really simple operators. So, you know, a series of tensors of S and S cubed, and they show that actually determining the code space in that case is NP complete. And so by implication, you know, you can't figure out the eigenspace dimensions without doing that first. And so it's actually NP hard to figure out the probability of the outcomes.
Okay, I see. So that's a carryover from the XS. I should take a look at that then. That's interesting.
Yeah, they do look at that quite carefully. So they've got a careful proof of it there. But yeah, as soon as you go to n equals 4 precision, yeah, you lose that efficient classical algorithm for estimating probabilities.
Let me see here.
Can you say a bit more on the Goddessman Canal theorem? That maybe were you planning to say something on that?
Yeah. Well, I guess my main point there was that the universe of operators where we are guaranteed to be able to measure efficiently is quite small. So basically, it's only the diagonal Paulis. So tensors of I and Z. So in general, that's the largest group we are guaranteed to be able to measure on any code space, any XP code space. And basically, it was just to reiterate the fact that, first of all, figuring out the probability of the outcomes is NP complete. And so, yeah, we're unlikely to have a classical algorithm for estimating the outcomes of measurements. But the other thing is that you're not guaranteed to stay in the formalism either if you measure certain operators. So, yeah, really, I can't see any way of generalizing the Goddessman Canal to this particular formalism.
Did you have a simple example for when the measurement takes you outside the set of operators?
I've got some in the paper. I could maybe pull up one of those if you really want to dig into it, or.
I mean, if you just, I looked through much, but it is a long paper, so I missed it. If you could just direct me towards where that was, I'd be interested in.
Yeah, no worries. I might just change the view here. Okay, so I'll just grab the paper. Yeah, so it should be chapter 7. So the measurements in the XP formalism. And then I think you should be looking at, example 7.3.
7.33. Okay.
Yeah.
Okay.
So that gives you an example of something that really ends up in something that cannot possibly be an XP state.
Ah, I see. Okay, that's very interesting.
Yeah. So you can still figure out what the final state is. You just can't show that it's an XP state. And then obviously as you get codes which are bigger and bigger, even figuring out the outcome probabilities gets very tough in general.
I see. Okay. Did we have any other questions? I'd like to thank Mark again, because this was a very interesting talk. He presented it very clearly. So I really appreciate that. Thank you very much, Mark.
Thanks, guys, and good to meet you.
Thank you very much. It was great to meet you. Thank you.
Yeah, great to meet you. Hope to look forward to seeing you again or discussing this material some more. So please.
Yeah, it sounds like there might be something interesting on that contextuality stuff. So
it seems like there's some unexplored sort of angles, low-hanging fruit there. So that would be something interesting to talk about.
Yeah. So if you guys get any ideas, feel free to get in touch, and I'll chat some more to Angela in our group, because she sounded quite excited when I mentioned contextuality. So
very good. Thank you, Mark.
All right. Thanks, guys.
Thank you very much.
See you later.
Bye-bye.